Okay, we're in section 4.2, antiderivatives and areas. So now what we're saying is basically there's going to be some kind of a correlation here. So our objectives are going to be to find the area under a graph and use it to solve real-world problems, and then to use rectangles to approximate the area under a graph. So some of our vocabulary, definitely something you've probably not seen before, something which is called a Riemann sum. And then we've also got summation notation, and then we've got definite integrals. Last time we dealt with indefinite integrals, so now we're going to add the definite integral into that. Okay, so if we look at the first objective that we had up there, finding the area under a graph and using it to solve real-world problems, apparently what that's telling us is there is some kind of a correlation to real-world meaning of the area under a graph. Now notice that this word under is in italics, and the reason it's in italics is because we say under, but what we really mean is below the graph but above the x-axis, or between the graph and the x-axis is probably the best way to say it. The reason that I kind of highlight that is because later on we're actually going to introduce a concept where we find area in between two different graphs, and that's going to help us, I think, with the overall understanding. So we say area under the graph, but technically under the graph, unless you stop at some place, like specifically at the x-axis, would really be infinite area because it would just keep going down. So that's what that means. Okay, really basic example, and we're going to kind of split this even example one up into two little parts here. If you were to take a highway trip, a road trip, and you drive for 45 minutes at 55 miles per hour, you could easily figure out how far you've gone. If I drove for 45 minutes and I was driving at a speed of 55 miles per hour, 45 minutes in hours is 0.75 hours. And then at 55 miles per hour, you would multiply those two things together, and what you would get is whatever 55 times 0.75 is. I'm not even going to try and guess at this point what that number is. I probably should have used 60 miles an hour. It would have made it a lot easier. But that's all you would have to do to figure out how far you've traveled. Well, what that represents on the graph here is we have traveled at 55 miles per hour. That's this line right here, this green line right here, 55 miles per hour. And we traveled that for 0.75 hours. So what you can see is that this red shaded section, which I'm going to go ahead and put in green stripes here, that shaded section right there gives us the amount of distance that we traveled. And then if we were to travel an additional 1.5 hours for 65 miles per hour, then we've gone a total of 138.75 miles. And all that is taking the first green area that I shaded, or the red area that I shaded with the green stripes, and adding to it everything shaded in blue, because that one was now at 65 miles per hour for the remainder of the time. If I take the areas of those two shaded rectangles and add them up, it would give me 138.75. Okay, so that's the general idea of one of the basic applications here, is we can find the total distance traveled if we know the speed or the velocity that we traveled and how long we traveled. Of course, and we're going to get into this, speed is not constant. We very rarely can hold a constant speed for more than a second or two. So we're going to deal with that situation in a little bit. Okay, example 2. So let's see, it says skateboards determines that for the first 50, it costs $40 per skateboard. What is the total skateboards? I guess, oh, okay, for some reason this got split. I apologize, I'm reading that all wrong. The words on the left of the graph go in line with the words on the right. So it's Greenleaf Skateboards determines that for the 50 skateboards produced, it costs $40 per skateboard. What is the total cost to produce 50 skateboards? Same general idea. 50 skateboards, which is down here, that's how many skateboards. It costs $40 per skateboard right there. I can figure out very easily just by multiplying 50 times 40 that we get 2,000. That is the area of that particular rectangular shaded region. So again, considering the graph to the right, we see, or the graph that's in the middle actually, we see that the computation is the same as finding the area of the rectangle. In both of those examples, the area under the graph represents the accumulation or total of a quantity. And of course, you might already be thinking to yourself, well, finding the area under the graph seems like an overly complicated method when all I have to do is multiply the two numbers together. What if, like I said before, in our example, Greenleaf's marginal cost was not a simple $40 per skateboard, but the marginal cost was this function right here, C prime equals that thing right there, which is a quadratic, which is graphed here on the left-hand side. This is no longer an easy geometric figure to find the area under. We could find the area of the stuff that was above because they were rectangles, which is easy. That's base times height, no big deal. This one is a little bit more challenging to find the area under. So what we're going to do is we're going to estimate this area first. We're going to estimate it by using rectangles. Okay, let's take a look at example 1. In this specific example, we're actually not going to need to use rectangles, and you'll see why in a second. So example 1, Cowsland Incorporated has a marginal profit function modeled by P prime of t equals 0.15 t, where t is in months and P prime of t is in thousands of dollars per month. Graph P prime of t and determine the total profit earned by Cowsland Incorporated in 1 year, or basically 0 to 12 months. So let's go ahead and do what it says. We're first going to start by graphing 0.15 t. That's just linear. The slope is 0.15, so every 0.15 that we go in the y direction, we go 1 unit in the x direction. It looks like this is not going to be too difficult to do, although I think I'm going to cheat just a little bit here. Let's see. I think I can do a line on here somewhere. I know I can do different shapes. Let's see. There we go. There's lines. Let's do that one. All right, so if I start at 0, if I go 0.15, that's going to be right about there. So it looks like it's basically just going to cross through all of these. It looks something like that. That looks pretty good. All right, so there is our graph of our marginal profit function. And now it says it wants us to find how much how much profit we earned in the first year. So basically we want to go from 0 out to here, out to 12, and then we want to find that area. Well, we don't need to use rectangles here because this is a triangle. We can easily find the area of a triangle, which is all this is. It's just the area between the curve and the x-axis, which is the area of that triangle. So the area of a triangle is 1/2 the base. Well, the base here is 12 times the height, and it looks like the height there was 1.8. So our profit over the first 12 months is going to be 1/2 of 12 times 1.8. So 1/2 of 12 is 6. 6 times 1.8, trying to do this in my head here, is, I think it is, let's see, 6 times 1.8. 6 times 8 is 48. Carry the 4. So 104. So 10.4. Okay, I think I did that right. And this profit would be in thousands of dollars, so it's $10.4 thousand. That would be our total profit. All right, so let's go ahead and take a look at another example. In this example, Greenleaf Skateboards has the following marginal cost function for producing skateboards. So for up to the first 50 skateboards, the cost is $40 per skateboard. For the quantities from 51 to 125, the skateboards cost drops to $30 per skateboard. And then after they've sold 125 skateboards, it drops to $25 per skateboard. If X represents the number of skateboards produced, we have the cost function, which is given as the piecewise, which is what we just read. So let's go ahead and graph it, and then we're going to find the total number of skateboards sold. All right, so it's constant. It's constant for each one of those intervals. We just have to do it on the right interval. So you'll notice in our case here that for the first 50 skateboards, including 0 and including 50, it's 40. So that means that up here, including 0 and including 50, the cost is always going to be 40. So that should be a straighter line. I should have just used that line function, but you get the idea. So there's the first one. And then it says once we hit 50 skateboards, from 50 to 125, the cost now drops to 30. So let's go ahead and drop the cost to 30. Notice now that's an open circle there because I can't have the cost be both 30 and $40 when I sold 50. So up to 50, it includes the orange dot, and then at 50, it's going to start with the green dot, but then go to the right. It does include 125, though. So it does include the 125. That's part of the domain there. So straight across here as good as I can. And then it's going to go from 125 to 150. It is going to be at 25. So open circle here, up to 150. Close circle out there. All right, so there's our graph. Now all we need to do basically is just create little rectangles out of these things and find the area. So we can easily do that. I'm just going to drop a dotted line here just to show where the rectangle would be. Drop the dotted line here, drop the dotted line there, and now all I have to do is figure out what the areas are. Well, again, it's really actually pretty easy. The first one is 40 times 50. 40 times 50. Then I have to add the second rectangle, which is 30 times, what is that, 75? That's my base. And then the last one is going to be 25 times 25. All right, so let's see. 40 times 50 is 2,000. 30 times 75 is going to be, let's see, what is that? 2,250. And then 25 times 25 is 625. All right, yeah, all that seems about right. And then we just add all this stuff up. So 2,000, let's see, 4,000, 4,250, 4,850, 4,875 would be the total number of skateboards sold. There we go. Okay, and in the previous two problems, or all the previous problems actually, we've been able to use geometric shapes, which are easy to find the areas of to be able to do the estimations. In this case, when we have a quadratic function like this, there is no easy geometric way to find the area of a quadratic. So what we have to do is we have to estimate the area using rectangles, and that is called a Riemann sum. And we're also going to introduce summation notation when we get down on the page a little bit further. So let's return to the question that we posed at the bottom of the first page. What if Greenleaf's marginal was this quadratic function which is shown here? The solution is actually pretty easy. We're going to use rectangles to approximate it. Now I say that it's easy, but the concept isn't that difficult. But what you should be able to see just from looking at the graph itself is that the rectangles that we're using, you should see that the rectangles are completely over top of the curve. So this is definitely going to be an over approximation using this. We're going to have over approximated this. So here, the estimate of the total cost of producing the skateboards, if we use in this case, 4 rectangles to approximate this, Again, you can see that there's a bunch of area up here which is over top of the curve, so it's really area which is over accounted for. There's a slight amount of area which looks like it might be under the curve here, but then there's also a slight amount over top of the curve here. That pretty much kind of cancels itself out, but there's definitely way more area above the curve than there is above and below. So here the estimate is going to be basically 50 times 100. That's the first complete rectangle, including that blue shaded region I did at the top. Then 33 times 100, then 22 times 100, then 17 times 100. Those are all the heights times the bases. So you get 12,200. Again, it's an estimation. What you hopefully can be able to figure out here is, what if I take those rectangles and I start to make them really, 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 really tiny, really infinitely thin? Well, the tinier and more thin that we make these rectangles, the closer our approximation is actually going to be to the area of that curve. Okay, now it's kind of hard to show it, but that's the general idea. Each one of the rectangles is going to have a width, and that's, in this case, the width is down here, is going to have a width of delta x. It's the change of x. Kind of miscircling that one, didn't I? Change of x. And that's going to be b minus a over 4, where b is the right endpoint. Here's b. A is the left endpoint. There's a. And then we divide it by 4. Why is it 4? Because we wanted to do 4 rectangles. If you wanted to do 100 rectangles, like it says up here, it would be very tedious to do, but you could. It would be b minus a over 100. Well, the point is, there's an easier way to write all this stuff out and to be able to figure it all out. There's ways to do this from the right hand and from the left hand endpoint of the rectangle. We're going to do sticking with the left hand endpoint in this particular case. All that means, by the way, is that the upper left hand corner of each rectangle is the part that actually touches the curve. You could do it from the right hand endpoint. In this case, it would actually give you an under approximation, but that's the general idea of what that means from right and left. So the area that we would get, again, it's the first f of x value. That's just a y value or a height. So this is kind of like your height. And then delta x is your base. So all we're really doing is a whole bunch of base times heights. Height times base. Height times base. Height times base. We're just adding up a bunch of rectangles. Well, it's obviously tedious, even the way I just wrote it there, f of x1 delta x plus f of x2 delta x. Again, if we had 100 of those, that would be a very long way to write it out. So we've come up with a shorthand notation, which is this thing which is called the summation notation. And what this says, anytime you see this capital sigma, which is a Greek letter, it means to add. You're going to add up a bunch of things. This piece down here tells us where we're going to start. The counter is going to be denoted by, in this case, I. It could be any letter. We use K. I've seen J. I've seen P. It just depends on what letter it is, so it doesn't matter. But that's your counter. And all it says is you're going to plug in, starting with 1, you're going to plug that in for all the i's that you have over here. We only have that one I. So what you would be able to see there is the first one would be f of x sub 1 delta x. And then again, the orange thing says to sum. So I'm going to add. Now you kick up that 1 to the next one, which is 2. So it would be f of x sub 2 delta x. And you would do that up until, oops, supposed to be a different color, up until you get to that number, which is 4. You always count by ones. The counters don't count by like 0.5s or anything like that. It's always whole numbers. And you would go up to 4. So you would have f of x sub 1 delta x, f of x sub 2 delta x, all the way out to f of x sub 4 delta x. If that number was 7, then you would go up to 7 and so forth. We'll do an example of that when we get to the next page. All right, so to compute an expression in summation notation, we write the terms by plugging in the values for I, which is what I just said, beginning with the number below the sigma. Usually it's 1. It can start at 0. It can start at something else. It just can't be negative. We can't start at a negative number. And again, it can't be decimals or fractions or anything like that. And then you're going to stop at the top number. So again, f of x sub 1, f of x sub 2, f of x sub 3, f of x sub 4. Those just represent the heights of the rectangle. Delta x divided by b minus a is going to give you the base of the rectangle for the width. All right, let's go ahead and go to the next page, and we will take a look at a couple of examples of this. Again, shouldn't really be that difficult. In the first one, what it says is, and sorry, not the first one, example 3, but in the first one of example 3, letter A, it says we want to take the sum as I starts from 1 and goes to 4 of 3i. I'm sorry, 3 to the I. So what that means is my sum, expressing this without summation notation, is going to be 3 to the first power by plugging the 1 in for I. Now we do the next one, plus 3 to the second power, plus 3 to the third power, and we're going to do this up until we get to 4, plus 3 to the fourth power. Now you can go ahead and simplify that if you want to, but it doesn't say to do that. It just says write it without summation notation, which is exactly what we did there. There will be times where we may have to simplify these things, but not in that case. Okay, the next one. Next one's going to be a little tedious. As you can see, we're going to start with I equals 1, but we're going to go up to 30, which means in order to write this out, you would technically have to write out 30 terms. We're not going to write all 30 terms. I'm going to show you a short way to do that. So typically what we will do is we'll start off with the first couple. So it'll be h of x sub 1 delta x plus h of x sub 2 delta x. That's enough to at least get the pattern started. Then what we're going to do is we're going to put plus dot dot dot, which means it's going to keep on going. And then we put a plus here, and then we're just going to put the last one. H of x sub is 30 delta x. What that means, that dot 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 basically means you're going to hold that pattern and continue adding all the h times x sub whatever delta x's all the way up till you get to 30. Just a shorthand notation of doing that. All right, a couple more examples. All right, in example 4, you could go ahead and plug this into your calculator just so you get an idea of what the graph looks like. It's not really necessary to do in our case. We want to use 5 subintervals to approximate the area under the curve of the given graph. So in order for us to do that, we need to figure out, first of all, it says 5 subintervals. So we need to figure out how far each subinterval is going to be. Well, remember that delta x, which is really the base of all of our rectangles, is going to be b minus a, which is 16 minus 1 over 5. Of course, 16 minus 1 is 15. So that gives us 15 over 5, which is 3, which means that the base of each one of our rectangles is going to be 3. Now what we have to do is we have to be able to figure out, okay, what are all the heights of my rectangles going to be? Well, I'm going to have 5 subintervals, and I'm going to be starting on the left-hand side with 1. So I need to figure out what f of 1 is. Okay, we'll figure that out, and we'll plug that in just a second. But then the next one is going to be f of, well, if I add 3 to it, because that's my delta x, it's going to be f of 4. We'll figure out that. That's the next height of my rectangle. Then we have to do f of adding another 3, 7. Then we'll have to do f of 10. And then we'll have to do f of 13. Notice I will not be using 16 because that already gives me my 5 rectangles. 16 would actually be a right-hand endpoint. So let's go ahead and figure these out. I'm actually going to pause the video here so I can plug all this stuff into a calculator. I'm not wasting your time. All right, so as you can see, all the values are now filled in. F of 1 is 34.8, F of 4 is 42.6, F of 7 is 30.6, F of 10 is 15, and F of 13 is 12, assuming that I plugged all that stuff in correctly. Now we're going to take each one of those and multiply them by 3 and then add them all together. And what we come out with is the Riemann sum gives us 405. So the estimated area for this beneath the curve and between the x-axis would be 405 from 1 to 16 using the left Riemann sum. Okay, so now let's go ahead. There we go. And look at our last example here. So we mentioned earlier that we could get a better and better approximation if the area under the curve was, we take greater number of rectangles. So if we were to take the limit of the Riemann sum as n approaches infinity, or the number of rectangles gets infinite, we're still going to get the exact area under the curve. So that's the whole idea. We're going to let the number of rectangles of the Riemann sums approach infinity. So we're going to end up taking a limit at the end. And that limit right here, the exact area, is the limit of the sum of all of the rectangles. Well, there's a shorthand notation of that, and it just happens to be the integral. Now what you'll see here is that this integral has numbers right here which we didn't have before. It's got a and b. Those are the bounds. It's just the bounds of the interval. So when we put those bounds into the integral, that now becomes what's called a definite integral. We're turning the sum into a definite integral where now we're actually going to find the area. So one more that we're going to do, and we've actually learned how to do this in two different ways. Well, we've actually learned how to do this in one way in this case. We're going to take the integral from 0 to 2 of 3x plus 2. Well, taking the integral is nothing more than finding the area. So what I can do is I can actually graph 3x plus 2 on my graph. Let's see, 3x plus 2 means that I'm going to have a y-intercept of 2, and then it's going to be up 3 and right 1. So up 3, right 1 unit is going to be about right there. Up 3, and then right 1 unit. It's going to be way out here. So it looks like my line, I probably should have just used the line tool, but I didn't. That was not too bad, actually. And we only want to go from 0 to 2. So that's going to be that right there. Well, what I've created here is I've created a trapezoid. Okay, it's another important geometric figure. The area of a trapezoid, is 1/2 base 1 plus base 2 times the height. And if you really think about this, if you were to cover up base 2 or base 1, it doesn't really matter, just cover it up with your finger, what you got is 1/2 base times height. If you think about it, a trapezoid and a triangle are very similar. The trapezoid just has that extra base that you have to add, that you have to account for the length. Now, a couple of things here with the trapezoid that you need to know, and then we're going to finish this up. It'll be really simple. In a trapezoid, the bases, while we're used to a base being on the bottom of the graph, the bases are not always like that. The bases are actually parallel to each other. Well, this right here represents a base, and this dotted line over here, which is now in blue, represents a base because they are parallel to each other. The red line that we drew for the graph and then the x-axis are not parallel to each other, so those cannot be bases. In this case, this is base 1 and this is base 2. Now the height of a trapezoid is perpendicular to both of the bases. So the red line cannot be perpendicular because it's not perpendicular to either one, but the x-axis is perpendicular to both of the bases. So the x-axis right there creates the height. So our height here is actually what we're used to being the base of rectangles, but in this case it's the height. So in order for us to find the actual area beneath this curve here, we just have to plug these values into the area formula. So it's 1/2. Base 1, it looks like it's 2. Base 2 over there on the right looks like it's 8. And then the height, which is actually the change of x distance, is 2. So we're going to get 1/2 of 10, which is 5 times 2 is 10. So that's the area that's created between those curves. We will actually be able to figure out how to take this integral algebraically in an upcoming section.